All right, welcome back. So I'm sure it probably looks as though my hands are really small.
Stubby, tiny fingerprints.
And I assure you, they're definitely not this small in real life. I actually just upgraded to a better marker board, and that's just, it's just the contrast. It's an optical illusion. Don't worry about it. It's all right. So today, what I'm going to do is I'm going to derive Euler's identity, one of my favorite mathematical derivations. And now that I have all this room for activities on this big marker board, I'm going to put it to full use now. So hopefully you all enjoy this. So first things first, what we're going to use to derive this identity is known as a Taylor series expansion, or Taylor polynomial. But we're going to center at 0. So arguably you could say that we're using the Maclaurin series convention. So that's how this is going to go. So that's basically the distinction. We're using the Maclaurin convention because it's centered at 0. So let's write out the formula and then we'll start going from there. So Taylor series expansion, what do we got here? So we got our function right here equal to our series. So the sum of all our n values to infinity and beyond. And then we're going to have our function raised to some nth power here. And then we're going to have that at our centered origin here. And then that's going to be divided by n factorial. And then, like before, x minus a to the nth power. Okay, so many of you might probably be looking at this and thinking, what the hell are you trying to tell me with this? Cryptic message are you trying to say? Well, I'm going to hopefully explain it piece by piece well enough for you to understand how every little part of this formula is applied. All right, so first what we're going to do here, we're going to go through piece by piece this whole formula just using the notation. Now, that's just to kind of get a sense for how this is going to progress for every term in the sequence. And we're just going to do it that way first, but then we're going to start expanding our exponential function afterwards. So you can kind of see how this is going to progress without just maybe throwing it all at you at once. So let's use the notation first, and then we'll start expanding our key functions for deriving Euler's identity, right? So we got our summation, right? And it's going to be nth terms to infinity. And we're starting at every term in the sequence, 0. So that's where we begin. For every first term in our sequence, we're going to have 0 here. So n is 0. And then we're going to have a, where it's centered, over 0 factorial. Now, I know I said we're doing the Maclaurin convention, but for the purposes of this demonstration, we're just going to have it a, just for now. But obviously, once I start expanding the actual functions, you'll see how that becomes relevant. So we're not also, just as an added disclaimer, we're not doing anything inherently wrong here. Dividing by 0 factorial, 0 factorial is 1. So you need not worry here. Now, we have our x minus a still, right? And that's going to be raised to the 0th power. Okay, so that's going to be to the 0th power. Generally, this doesn't stay within our sequence just because anything to the 0th power is just 1, except for infinity. That's indeterminate. Now, we're going to add plus, and then we're going to have our next term in the sequence, where we have 1, and then a over 1 factorial, then x minus a raised to the 1th power, right? Which is just this term here, right? So we're going to have our next one, we'll do one more, and then we'll start expanding our functions. So we're going to have our second one, and it's 2 here, centered at a over 2 factorial, and then that's going to be x minus a raised to the 2nd power. Okay, and that's just going to go on forever, right? So this is what it's going to look like, essentially, when we start applying our functions. So you can kind of see how this is kind of working piece by piece. So hopefully that maybe painted a little bit better of a picture so it doesn't seem as obscure when I start applying the actual function, right? So now that we've gotten that out of the way, let's start expanding our function and get rid of this clutter, and we'll start actually deriving Euler's identity. So. Okay, so we have our function all laid out here, e to the x. That's what we're going to be expanding first. And generally, when you are beginning to expand a function using the Taylor polynomial formalism, you want to take the derivative at least 4 times before you start proceeding with the expansion of the series here, or of that function. So this is not inherently necessary for this purpose, just because e to the x is its own derivative, so it's kind of a waste of time. So it's just going to be the same thing every time. So for this purpose, it's not necessary. So with that being said, remember, we are starting at 0, and since we're using the Maclaurin series convention, we are centered at 0. So a is going to be 0, right? So a is 0, and we basically just need to expand from there. So just keep in mind that a is going to be x in this situation. That seems a little weird, but maybe I should have put a there, but hopefully that's not too obscure here. But let's just go on. So remember, we're staying at 0, leaving this out because it's irrelevant for e to the x. So we're going to have 0 right here, and e to the x is going to be 0, and this is going to be 1, right? So we're just going to have 1 over 0 factorial. So that's basically our first term. And it's just going to be 1, obviously, because 1 divided by 0 factorial is going to be 1. So next term, we're going to have, remember, we're starting at 0, so e to the x, that's going to be 1. And then we're going to have this over 1 factorial. And this is going to be x minus a to the nth factorial, and a is 0, so it's just going to be x to the 1, right? So that's our first term. So, or our second, sorry. And then our next, we're going to apply the same thing. And I think at this point, you're probably starting to get a feeling for the pattern, but you'll see if you haven't yet. So next one is going to be x minus a is 0, so we're raising that to the second power. That's going to be over 2 factorial. Okay, no big deal. So let's do our next one. We're going to have x to the third now over 3 factorial. Now, if you, I'm sure at this point you're seeing the pattern. It's literally sequential. So, and this is going to be plus x to the 4th over 4 factorial plus x to the 5th over 5th factorial. And then I'm just going to do that. It goes on forever, right? So basically, what this is telling you is you're getting a closer and closer approximation for e to the x. The more terms you get, the closer you actually get to this term. All right, so now what we want to do is bring in our friendly neighborhood trig functions. So this is when it becomes relevant that we're centering our function at 0, all right? So let's just pull one out of the hat, cosine, right? So we're going to use cosine. So g of x is equal to cosine of x, right? All right. So now this is when it becomes relevant to start taking the derivative, at least 4 times. And you'll see why it's 4 times in a moment. So first time, we're going to do g prime of x is equal to, well, the derivative of cosine is just negative sine. So negative sine of x, and then we're going to have g double prime of x is equal to, well, derivative of negative sine is going to be negative cosine of x. And then g triple prime is going to be equal to sine of x. And g quadruple prime, if you will, is equal to, well, we're just back to where we started, back at cosine. So that's why we're doing it 4 times. It just loops. So we're going to have cosine again. Okay, so now, before we start expanding, since we're centered at 0, let's just start applying 0 to all these functions and see what that yields. So cosine evaluated at 0 is just 1. Negative sine of x evaluated at 0, well, that's just 0. Negative cosine of x evaluated at 0 is just -1. And then sine of x evaluated at 0 is 0 yet again. And then back to where we started at 1. All right, so now we can start expanding. So let's start doing that. So cosine of x is going to be, all right, so expanding this here, since we are going to have our first term at 0, we're going to be using this one, right? So basically, this is going to be raised to the 0 power. So remember, that just kind of omits from the sequence. It's not really necessary since we're just multiplying by 1 at that point. So then we're just applying our function of our first derivative that we took, centered at 0. And we're going to have 1 over 0 factorial. Just going to leave it there for now. And next term, we're going to have plus. Well, now we have 0, so it's not really all that necessary to keep this term in the sequence, but for the sake of consistency and keeping things in order, I'm just going to leave it so it doesn't make things look a little strange, right? So we're going to have, well, we're going to have 0, and this is going to be x to the 1 now, right? X to the 1 over 1 factorial. Like I said, this is obviously going to cancel in the end, but just to kind of keep this thing going successively here. So we're going to have our next term, and that is going to be g double prime, right? And as you can see, we got a negative here, so this positive isn't necessary. So we can do minus, and now we're going to have x raised to the 2 here, right? So x squared over 2 factorial. Okay, so now we have that. So let's move on to our g triple prime. That's going to be 0 again, but I'm just going to leave it. So we're going to have plus 0 times x to the 3rd over 3 factorial. And then our next term, back to where we started. And we're going to have plus x to the 4th over 4 factorial. So obviously you might be picking up the obviously you might be picking up on the pattern at this point. And if not, let me sort of elucidate that for you. So this is going to be 0. This is going to be 0. And what we're left with is just 1 plus, or sorry, 1 minus x squared over 2 factorial. Keeping that term right. And then this term plus x to the 4th over 4 factorial. And this is going to be interchanging now. We're going to have minus, plus, minus, plus, minus, plus. And we're using odd squared terms, right? So we're using even exponents. So we're going to have minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus So even powered terms, because cosine is an even function. Makes sense, right? So now what we want to do is apply the same game, but with sine this time. So since we're using sine, we're going to apply the derivative in the same way and then expand it all out. So I'm going to get rid of this and then we're going to expand the rest of it. All right, so we got our sine of x now. Let's start applying the derivative and then expand it, right? So we're going to have h of x equal to sine, and then h prime of x is going to be equal to negative cosine. Or that's going to be cosine, sorry. That's going to be cosine of x. And then the h double prime of x is equal to negative sine. And then h triple prime is equal to negative cosine of x. And then h quadruple prime, and that's going to exactly what we started, right? So sine of x. And we'll start applying our centered value, our a value here. So 0, that's going to be equal to just 0. And this is going to be 0, 2, equal to 1. Apply this. We're going to get 0, and then this is going to be negative 1. Then here, 0 is going to be equal to 0. Interchanging, sort of. So, next time. So now we're going to expand it. We're going to have sine of x equal to, so our first term in the sequence is going to be 0, right? So, obviously this term is not going to be left within the final product, but I'm going to leave it, right? Just like before. So we're going to have 0. That I'll get rid of. It's not really necessary here. That's just going to be 1. So we're going to have 0 over 0 factorial. That just doesn't look right. I don't know. But all right, so next let's do our h prime, right? So plus. So we're going to have plus 1. And that's just going to be x. So x over 1 factorial. Then our next one, well, that's just going to be 0 again, right? So 0 x squared, obviously it's going to cancel in the end here. And we're going to have 2 factorial. And then let's move on to h triple prime. And then we're going to have minus now, since we have the negative. And that's going to be 1 times x to the third now over 3 factorial. And then back to where we started, we're just going to have 0, of course. So that's going to be 0 times x to the fourth over 4 factorial. And then if you haven't picked up on it at this point, so let me sort of show you how that looks. So this is going to be canceled, right? That's going to be 0. That's going to be 0. And we're going to have all odd terms now, right? Because sine of x is an odd function. That's how that works. So we're going to have this equal to x, since that's just going to be x, because 1 factorial is just 1. And then we're going to have minus x cubed over 3 factorial. And then we're going to have plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus right? So we got all our odd terms. We're almost there, almost to the grand finale. So now we have this. Let's sort of, consolidate that all over there, and then start throwing a little bit of a twist into the mix here, right? So let me get rid of that, and we shall proceed. So now what we want to do, now that we've gotten all that situated here, we want to bring in our imaginary friend from the complex plane, I, right? So what is I? I is just the square root of -1, so that's I, right? That must mean I squared is equal to -1, right? So using that idea, we're going to sort of do this in a similar fashion, right? So we're going to have I. So I to the 1th power is equal to 1. Well, as we've established, I squared is equal to -1. And then I cubed is equal to, well, I squared times I, which is just equal to -I. And then we're going to have I to the 4th power. And that's just I squared times I squared, which is 1. So this is what we want to use. And we are going to throw this into our new expansion. We are expanding e to the x again. So e to the I times x this time. So let's start moving on forward with the same idea, right? So obviously if we're just taking this to the 0 power, I to the 0 power is still 1. So that's why it's not in this first term. So 1. And then we're adding that. So now we're going to have I times x, right? Since it's going to be I to the 1th power, which is I. I don't know why that looks. That's I. It's not 1. So I have to But yeah, so we're going to have I times x plus our new term. So I times x squared over 2 factorial. And then we're going to have that plus, now we're going to have I times x cubed over 3 factorial plus I times x over 4 factorial plus, let's do one more here, I times x to the 5th factorial, or to the 5th over 5 factorial, plus dot dot dot. Alright, so now we should apply this operation to all the I values in the parentheses, right? So that's going to give us 1 plus I times x. And remember, I squared is just negative 1. So we're going to have minus x squared now over 2 factorial. Now we're going to have I cubed, which we've established is just negative I. So we're going to have minus I x cubed over 3 factorial. Then I x to the 4th power. I to the 4th is just 1. So we're going to have plus x to the 4th over 4 factorial. And then I times x raised to the 5th power. Well, it just loops back in on itself, back to I. So we're just going to have plus I times x to the 5th power over 5 factorial minus x to the 6th over 6 factorial. And dot, 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 dot. And that's going to be, yeah. Okay, so, and I'm sorry, that would have been a negative. Okay, so, now what we want to do is isolate our I values and isolate our terms that don't have I. We're just going to sort of demarcate them, if you will, and then put them in their own separate little brackets. And we'll go from there. So now, if we're going to separate these out, we're going to have e to the I times x is equal to, so we're going to have our bracket. So let's take all of our non-I values first, right? So we're going to have 1, because that doesn't contain an I, minus x squared over 2 factorial. That doesn't contain an I. Then we got x to the 4th plus x to the 4th over 4 factorial. Then x to the 6th over 6 factorial minus. And I'm sure you might be noticing this pattern now, right? And that's going to be plus, dot, 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 bracket that off. But before we start making any judgment calls, let's do our next set of terms. And we're adding that to our I values now, but we're going to extract our I. So we're going to pull that out, and we're going to have I, and then bracket off these, and then we're going to have x, because that had an I, right? And then our next one, minus x cubed over 3 factorial. And then we're going to have I times x to the 5th, right? Plus, oh, sorry, I don't need the I. We're just going to have x to the 5th over 5 factorial. And you might be noticing how this is going now, right? So we're going to have minus all the odd terms. So we're going to have x to the 7th over 7 factorial plus dot, 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 right? We'll bracket that off. All right. So what we have here, in fact, are precisely what we just expanded, our trig functions, right? This, in fact, is just, don't make fun of my delimeters, I'm very insecure about them. We're going to have cosine of x here, right? And that is plus what we have here. Well, that is simply our sine function, right? So we're going to have I times sine of x, since we have all of the odd terms, right? All right, so we have just proved that e to the I times x is equal to cosine of x plus I times sine of x. That to me is pretty cool. I mean, it's simple, it's elegant, and that's not the whole picture yet. There's an added little bonus, little cherry on top, if you will. What we're going to do now is replace x with pi. So let's change x to pi. That is going to be equal to cosine of pi now, right? Sorry. It's going to be cosine of pi now plus I times sine of pi. And, well, what is that? Well, this is just going to be -1, right? -1 plus, well, I times, well, the sine of pi, that's just 0. So we're going to have 0. This is going to cancel, and our final result is, if I bring this 1 over, we're going to have e to the I times pi plus 1 is equal to 0. And there you have it. E to the I times pi plus 1 equals 0. All of the fundamental pieces of mathematics that you see in one simple, elegant equation. So you may be asking yourself at this point, does this formula have any practical applications outside of just being just aesthetically pleasing for the sake of it? And absolutely, it's very, very useful in many, many different areas of physics. Now, one that generally is the focus of this formula happens to be within electrodynamics. And electrodynamics uses alternating currents, which is also within almost every piece of technology that we have. And it's very helpful to use this formalism because you treat this alternating current as a complex wave. And when you do that, it makes the mathematics far more simple than they otherwise would have been. It's also very useful within transformation calculations when you're using Fourier transforms and converting from a frequency domain to a time domain. It just makes things a lot more simple. And for that reason, this formula is not just aesthetically pleasing, it is very useful for that reason. So with that being said, I am very grateful that you guys have watched, and I really hope you kind of stick with this. I know it's been a while, and I'm sure you've been losing tons of sleep over me not releasing any new content, and I understand. I would too, don't worry. I will start releasing more. Chances are they'll be a little more physics related, and just stay tuned, and I will grant you with all the nerdy content your heart's desire. Thanks.